This is the second of two lectures on line integrals. In this lecture, we're going to consider line integrals of vector functions in the plane and in space. So we'll learn how to compute line integrals of a vector function in the plane. That's a vector function of two variables. And we'll learn how to compute line integrals of a vector function in space. So that's a vector function of three variables. And again, we're integrating these vector functions over plane paths in 2 dimensions or space curves in 3 dimensions. So let's take stock of what we've done and where we're going. In the last lecture, we talked about line integrals of scalar functions over plane curves and space curves. Today, we're going to talk about line integrals of vector functions over plane and space curves. If C is a curve in the plane, we've already seen how to compute the integral of f with respect to arc length, either in the plane or over a space curve. And we've also defined integrals like the integral of a function of two variables with respect to x, but over a curve, or the integral of a function of two variables with respect to y, but over a plane curve. So today we're going to define two new kinds of integrals. The integral of f dot dr. F is a vector-valued function. C is a curve. We'll define it over the plane and over space, where f is a vector function of three variables, and C is a space curve. Why are these integrals important? They arise in various contexts in physics and other kinds of applied science. The most basic one is that a line integral like this measures the work done by a non-constant force moving through a path C. And there are other quantities, one of which we'll see in the lecture, the circulation of a non-constant electric or magnetic field over a path in space. These ideas turn out to be important, for example, in the formulation of Maxwell's equations of electrodynamics, which are fundamental in the study of electromagnetic waves. So let's begin by remembering what space curves are and how they work. That's going to be important for us. Remember that a space curve is a function of t. It's a vector function of t. It has components x of t, y of t, and z of t. And we learned way back in Unit 1 that the tangent vector to a space curve is the new vector function you get by taking derivatives of the component functions x, y, and z. The magnitude of the tangent vector is the speed. The tangent vector itself is a velocity vector. The unit tangent vector is what you get by dividing the tangent vector by its magnitude. So the unit tangent vector, denoted by a capital boldface T, is a vector of unit length, which is tangent to the space curve at that particular point. So just as a checkpoint to remember, take a minute now and see if you can compute the tangent vector and unit tangent vectors to the curve that I've given you at times t equals 0, t equals pi over 2, and t equals pi. Let's go through the calculation of the tangent and unit tangent vectors for the curve that I've now shown in the left-hand side. And I've also marked the 3 points where t is 0, t is pi over 2, and t is pi, as well as shown what the tangent vectors actually look like. So this is a part of a helix curve. Let's first of all calculate the tangent vector as a function of t. Differentiating the components, I get minus sine t times I plus cosine t times j plus 1 times k. That means that the magnitude of the tangent vector, that is to say the speed, is root sine squared t plus cosine squared t plus 1, so I'm just taking the sums of squares of components, and that's just root 2 because sine squared plus cosine squared is equal to 1. That means that the unit tangent vector which is just the tangent vector divided by its length, is 1 over root 2 times negative sine t I plus cosine t j plus k. If I now evaluate at the various points at t equals 0, the tangent vector r prime of 0 is, let's see, the I component 0, the j component's 1, and the k component's 1. That means that the unit tangent at 0 is just the normalized version of that vector. And sure enough, let's see, if we look at the picture, here's this unit tangent vector, and it has no component in the x direction, but it's going diagonally upward at a 45-degree angle, parallel to the yz plane. What about when t equals pi over 2? The tangent vector at pi over 2, going back to the formula for the tangent vector, that's minus I plus 0j plus k, or minus I plus k. The unit tangent is just the same vector normalized. So let's make a little bit of room so that we can write down that the unit tangent vector at pi over 2 is just minus I plus k over root 2. Finally, when t equals pi, the tangent vector at pi, going back to the original formula for the tangent vector, is, let's see, minus sine of pi is 0, so there's no I component. Cosine t times j is going to be minus j plus k. Now again, that looks about right. We're decreasing in the y direction and increasing in the z direction, so that looks like that's what this vector here is doing. Finally, the unit tangent, capital T at pi, is just the normalized version of this vector. So we have that factor 1 over root 2 multiplying minus j plus k. Now I'd like to consider the work done by a force on an object if the force varies over space and acts over a certain path. So we know what the rule is for work if a constant force acts through a fixed distance. Force is a vector, displacement is a vector, work is a scalar, which is the dot product of force and displacement. The component of force along the direction of displacement that matters. What happens if F and D vary as the force acts through a curve C? In this case, I want to take the curve over which the force acts, and as the diagram indicates, I'm going to divide it into little pieces. In each one of those pieces, the displacement is roughly the unit tangent, T, times the arc length of the little segment. So that's a vector, right? Delta S is a scalar, T is a vector. So the displacement is tangent vector, unit tangent times delta S. Now I want to divide the path into equal segments, as I've already indicated, and on each one of these segments, on each one of these guys, I'm going to pick an X somewhere in the little blue segment. Pick an X, Y, and a Z, and evaluate the force there. Then dot with the unit tangent times the arc length of that segment. So on each segment, the force is approximately constant, and I can use this formula for a constant force as an approximation, where the displacement is given by the unit tangent times delta S. That means, of course, that the displacement changes direction in these different segments, but that's fine. I'm going to add up over segments. So the total work done is going to be the sum over these segments of force times displacement. This sum, the approximation, is the Riemann sum for a certain integral over the curve, the integral over the curve C, of the dot product of F, the force, and T, the unit tangent, integrated with respect to arc length. So actually, this new integral is, when you look at it closely, something we've already done. I take the scalar function F dot T and I integrate with respect to arc length. That's the work done by a force that varies in space when the displacement is over a curve C. So I now want to focus on this formula and an easier way of evaluating it. Again, any new integral that we meet here, we're going to find a way to reduce to a calculus 1 problem. In order to compute this new line integral, we need to remember some facts about space curves, their tangents, and their unit tangents. So if the space curve is parametrized by functions x of t, y of t, and z of t, remember that the unit tangent is just the tangent vector divided by its length, and remember that the arc length is just the magnitude of the unit tangent times dt. So why is that true? Remember that the arc length, r prime of t, is just the square root of sums of squares or of components, which for a space curve in 3 dimensions looks like this. And remember that the arc length is exactly that same quantity. Dt. What that means for us is the following thing. When we go to compute the integral of a vector function over a curve, this is our formula for that integral. How do we do that? By parameterization. If the curve C has this parameterization for t running from a to b, then this integral is going to be the integral from a to b of f evaluated along the curve dot the unit tangent times ds. But what you'll notice is that the highlighted functions in cyan actually cancel. And we're left with the following integrand. We're left with a vector function of t, the force F evaluated along the path, dotted into another vector function of t, the tangent vector, and the result is a scalar function of t integrated from a to b. So again, that's a calculus 1 or calculus 2 problem. Let's pick an example and work out the new line integral. We're going to suppose that the force is given by this formula and that the path is parameterized by the formula given for values of the parameter t between 0 and 1. So how do you lay out a problem like this? First of all, we need to compute the tangent vector, r prime of t. That's going to be 3t squared I minus 2tj plus 1 times k. On the other hand, if I evaluate the vector field along the curve, what does that mean? That means I substitute the parameter functions x of t, y of t, and z of t into the formula for f. And what I get is the sine, let's see, x of t is t cubed, sine of x of t times I, plus the cosine of y of t times j, plus x times z times k. So x is t cubed, z is t, so xz is t to the 4th. And now I'm supposed to form the dot product of these two vector functions. So f of r of t dot r prime of t is going to equal 3t squared sine of t cubed minus 2t cosine of minus t squared plus t to the 4th So that's the dot product. The integral I have to do then is the integral over this curve of f dot dr is equal to the integral from 0 to 1, that's the parameter range, of 3t squared sine of t cubed minus 2t cosine of minus t squared plus t to the fourth, all that dt. Let me call these integrals 1, 2, and 3. The first two integrals are excellent opportunities to use integration by substitution. For on integral number 1, I can make the substitution u equals t cubed and du is 3t squared dt. Making the substitution both in the integrand and in the limits, I see that the first integral is just the integral from 0 to 1. 0 cubed is 0, 1 cubed is 1. Of sine of u du. The antiderivative there is minus cosine of u. I'm supposed to evaluate from u equals 0 to u equals 1. And so what I get is 1 minus the cosine of 1. And that's integral number 1. For integral number 2, again, there's a natural substitution. U equals minus t squared. Du equals minus 2t dt. So making the substitution both in the integrand and in the limits. Let's see, when t is 0, u is 0. When t is 1, u is minus 1. What I'm integrating is the cosine of u du. That antiderivative is the sine of u from u equals 0 to u equals minus 1. And what that works out to be is the sine of minus 1 or minus the sine of 1, since the sine is an odd function. Integral number 3 is easy. That's the integral of t to the fourth, and we know that's just 1/5. So when I add up 1, 2, and 3, what I get is 1 minus the cosine of 1 minus the sine of 1 plus 1/5, which is 6/5, minus the cosine of 1 minus the sine of 1. Now we come to checkpoint 2. So what I'd like you to do is use this nice formula for computing the line integral of a vector field over a curve to find the integral of this vector field over this curve where the parameter goes from t equals 0 to t equals 1. The first step in setting up this problem is to find the tangent vector r prime of t. That's 2ti plus 3t squared j plus k. Then I need to evaluate the vector field along the curve. Let's see, f of the x component is x, which is t squared. The y component is y, which is t cubed. And the z component, or the k component, excuse me, is z, which is just t. The integrand of the integral I'm going to compute is the dot product of the vector field evaluated along the curve with the tangent vector. And so I can read that off. The I components give 2t cubed. The j components give 3t to the fifth. The k components just give t. So the integral over the curve C of f dot dr is the integral from 0 to 1. Remember, that's the given range of parameters. The integrand is 2t cubed plus 3t to the 5th plus t. Then evaluating the integral, it becomes pretty much a problem of adding fractions. So the answer is 3/2. Next, we come to the last checkpoint of the lecture, checkpoint 3. After all, the whole point of introducing these new sorts of line integrals is to compute work. So I'd now like you to compute the work done by this force field on a particle that moves around this circle in the counterclockwise direction. So remember, that's that away. So you need to parameterize this curve, and you need to set up the line integral of this vector field over the curve. Let's compute the line integral from checkpoint 3. First of all, we can parameterize the path. The circle in the counterclockwise direction, it's a circle of radius 2. We can use the cosine and sine parameterization. That means the tangent vector looks like this. I need to evaluate the force field along the curve, which means I substitute 2 cosine t for x, and 2 sine t for y. Then I take the dot product of the force field evaluated along the curve with the tangent vector. What that gets me is the following function. Again, where did things come from? Just to make it clear what's going on, I take the dot product of this component with this component to get the -8 sine t cosine squared t. And I take the dot product of this component with that component to get the 8 sine t cosine squared t. And what I notice is that the integrand is actually 0. So it's easy to see that the integral over this curve of the force with respect to r is 0. How could I have seen this result coming? Let's examine this vector field a little bit more closely. Every time an arrow crosses the circle, it looks like it's perpendicular. No matter where you look, this vector field is always perpendicular to the circle. So that means that the dot product in the line integral is always going to be 0. So it shouldn't surprise us that the integral turns out to be 0. I want to look at an application of these line integrals in physics. Ampere's law is a principle of electrodynamics that says that if you have current flowing through a wire, so the blue thing is supposed to be the wire, that current flow generates a magnetic field, and Ampere's law says that that B field, in the case of this situation with this symmetry, axial symmetry, there's going to be a B field around the current carrying wire where the components of the field are always perpendicular to a line going from the wire to a circle. So there's a kind of circulation of the vector field. And indeed, another name for this kind of integral is what's called the circulation of the vector field along the curve C. Ampere's law says something very precise about that integral around a circle. It always must be a physical constant times the current being carried. So the question is, what is the magnitude of the magnetic field at a distance r from the wire? And to figure that out, let's think about what this circulation integral must be. So let's remember this definition of the line integral. Remember, with the unit vector t. Since the B field is tangent to the path, this is going to be really just the integral over the curve of the magnitude of the B field integrated over arc length. So what is that? The magnitude of the B field is a constant, and the integral over the arc length is the perimeter of the circle, so that's 2 pi r. According to Ampere's law, that's equal to mu naught times I. So this is the point where we use Ampere's law. So taking this equation, I can now deduce what the amplitude of the magnetic field is, just by dividing by 2 pi r. It says the magnitude of the magnetic field is the physical constant times the current flowing over 2 pi r. In other words, the field strength falls off like 1 over r as you move away from the wire, which makes a certain amount of physical sense. So this is an example of how line integrals get applied in physics. Let's summarize the line integrals that we've seen. We talked about the line integral of a scalar function over a curve. Here I've given the version for space curves. Remember that you have to evaluate the function f along the path. ds is given by this expression, that's the arc length element. So we talked about the integral of a scalar function over a curve with respect to arc length. We also talked about the line integral of a scalar function over a curve with respect to either x, y, or z. In one case, dx is just x prime of t dt in the parameterization. dy is y prime of t dt. And dz is z prime of t dt. The new line integral that we introduced today was the line integral of a vector field f over a curve c. What that is, if the parameterization goes from a to b, is I evaluate the vector field f along the curve, then I take its dot product with the tangent vector and integrate over t. So what we've done today is we reviewed line integrals of scalar functions from last time, and by finding an expression to compute the work done by a non-constant force over a path c, we defined the integral of a vector field over a curve.